To today's afternoon session. Our first speaker is Norton Lee from Institute for Basic Science. He obtained his PhD degree from Stony Brook University in 2021, and he received the 2025 Frontiers of Science Award for the work that he will be presenting today. Let's welcome Norton.
Hello, can you hear me? Yeah. So I'm very honored to receive this prize to talk about this work that I've done in the end of my PhD career. So the topics I'm going to talk about is defect in gauge theory, quantum spin chains, and Knizhnik-Zamolodchikov equation. The title is slightly different from the title of the paper because eventually we add on a little bit more. So this talk was based on the award-winning paper and 2 more follow-ups. Here's a quick outline. So I have a quick introduction on the some background. So the paper is actually related to 3 subjects in theoretical physics. You have a supersymmetric gauge theory, you have an integrable system, and then also you have conformal field theory, 2-dimensional conformal field theory. So I will introduce all 3 of them. So first, I will give you a quick review on the 4-dimensional n equals to 2 supersymmetric gauge theory, or SQCD. And then we'll do the defect part. We'll introduce 2 types of defect to the gauge theory. And then we will link it to the first part, which is the quantum XXX spin chain, which is a quantum uplift of the 1-dimensional Ising model. And then we will also link to the CFT part, that's the Knizhnik-Zamolodchikov equation. And I will give a brief summary at the end. So let's start with the introduction. So through the wealthy structure of the duality in string or M theory, we found that supersymmetric gauge theory, usually you can embed it into string theory with certain, with a particular brane construction. So supersymmetric gauge theory with 8 supercharges, which means you can be either 4D n equals to 2 or 5D n equals to 1, etc., etc. Often finds correspondence to somewhat distinctive and seemingly unrelated subject. So you can see this graph here. You can embed your supersymmetric gauge theory in a lower dimension, 4 or 5, or even 2 or 3, into an M theory or string theory that's 10-dimensional or 11-dimensional. Now, on the other direction, you have some other kinds of theory, like conformal field theories or even integrable systems, which also embedded in the same string theory. So if you walk past through the string theory part, then you establish the correspondence between the 2. Now, the most noticeable correspondence are in 2 categories. The first one is called BPS CFT correspondence. So the idea is you establish a relation between a 4-dimensional supersymmetric gauge theory and a 2-dimensional conformal field theory. This correspondence was first observed in n equals to 4. So this is a very special case because you actually have 6 supercharges instead of 8. And then it's found in n equals to 2, followed up by the well-celebrated AGD conjecture, which established a bunch of correspondence between many supersymmetric gauge theory and the conformal field theory. And finally, in recent years, we started to move a little bit further. We can solve for the so-called KC or BBC equation of the conformal field theory from the gauge theory perspective. The other well-celebrated correspondence of this relation is called best gauge correspondence. It's a relation between the integrable system and the supersymmetric gauge theory. So the well-established cases include 4D n equals to 2 super Yang-Mills theory, which is in correspondence to so-called Toda lattice. And then another case is the 4-dimensional n equals to 2 super QCD, so which means you have fundamental matters. In that case, it corresponds to a so-called XXX spin chain in Gaussian model. So this is actually a supersymmetric gauge theory which duals to 2 different integrable systems, which are spectral due to each other. You can do a little bit more if instead using a fundamental matter, you add adjoint matter. You have the so-called 4D n equals to 2 star theory. And it's related to the so-called Calogero-Moser system. So it's again a one-dimensional system, but now your potential is a Weierstrass P function. So in the first glance, you will think, oh, the theory is highly nonlinear, it should not be solvable. But it turns out it's an integrable system. Now, instead of a 4D, you can actually go one-dimensional further. You have 5D n equals to 1 theory, compactified on the circle. So you still have 8 supercharges. So in this case, if you again goes back to the super Yang-Mills, you just have the vector multiplet. It corresponds to the so-called relativistic total lattice. So here you can see there's a parallel here between the 4D super Yang-Mills and 5D super Yang-Mills. And then if you do 5D n equals to 1 theory with SQCD, so which means you add fundamental matter, the integrable system that you got is an x-axis Z spin chain. Actually get 2 x-axis Z spin chain. So if you look at the correspondence, you will even say like the x-axis Z spin chain is a relativistic version of the x-axis spin chain. So in the paper, we propose an interesting BPS CFD correspondence playground. The correlation function of the two half BPS surface defect in the 4-dimensional n equals to 2 supersymmetric gauge theory with SUN gauge group with 2n fundamental matters. So this is the theory that we are discussing. We identified the correlation function with 2 objects. The first one is actually a 5D, is a 5-point conformal block. So if you do a Fourier transform of this correlation function in the gauge theory, it gives you a 5-point conformal block of the so-called SLN current algebra, which I will introduce in a moment. And also, we found that the same correlation function is a state of the XXX Heisenberg spin chain, which I will also introduce in a moment, in the so-called Heisenberg-Weyl module. So this Heisenberg-Weyl module is special because it's by infinite. So you don't have any state which is eliminated by the raising or the lowering operator. Now this talk is mainly based on the following 3 papers. So the first one is the award-winning paper called Intersecting Defect. The second one in 2023 is the Parallel Defect. And the one that published last year, 2024, is a further extension of the 2. So let me start. So the supersymmetric gauge theory we consider here is a 4-dimensional n equals to 2 super QCD. It's an A1 gauge theory, which means you have a single gauge field. And we put it in the gauge theory to be SUN with 2n, so 2n hypermultiplied in the language of the supersymmetric gauge theory. The Lagrangian is parameterized by the complex gauge coupling. So here you see how. So here the 4 pi over g squared is the familiar gauge coupling that you learn in quantum field theory. And then you have something called the so-called theta angle. You can exponentiate your complex gauge coupling and we'll call it Q. And also because you have fundamental matter, and those fundamental matter will have masses, which we split into 2 categories. You have n fundamental and n fundamental, which are labeled by n plus and n minus. So here you already have 2n plus 1 parameters for you to play with. Now, when we consider this theory, we're looking at the so-called Coulomb branch. Now, in the Coulomb branch, there's a choice of vacuum that we are allowed to make, which gives you the same energy of spectrum. So the choice of the vacuum is parameterized by so-called Coulomb modular parameter A. So again, it's n complex parameter. If you do SUN, then you have an additional constraint that all the n sums up should be 0. And finally, for localization purpose, we'll introduce so-called omega background, which will introduce 2 more parameters, epsilon 1 and epsilon 2. Now there's a type 2A brane construction in string theory for the theory that I mentioned. So you can consider this N5D4 brane configuration, where the NS5 will occupy the first 6 dimensions of your 10 dimension. And the D4 occupies the first 4 and then 1 separated one. Now, if you plot it in a way you isolated out the 4, 5, 6, and 7 direction. Then you have the 4 and 5, which goes in the vertical direction, which are the two NS5 brane. You have n finite D4 branes suspended in between that give you the modular parameter. And then you have two n set of semi-infinite D branes, D4 branes extended from one NS5 brane to the infinity. So that will correspond to the 2n fundamental matter. Now, when we are doing quantum field theory, one important subject that we study is the partition function. Now, the partition function will include the one loop part and the tree level part. In particular, it will have the non-perturbative part. Now, the non-perturbative part is so-called the instanton moduli space. So instanton is given by F equals to F dual in 4 dimensions. And now, thanks to supersymmetry, we found that it's very easy to find that the integrand is actually 1, and you integrate over the so-called instanton moduli space, which can be systematically constructed by the so-called ADHM construction. Here's the bad part. So if we look at the integration, it just tells you it's the volume of this space. But this space is actually infinitely large. So you integrate, if you just do the integration straightforwardly, you get something which is infinitely large. It doesn't tell you anything. So in this way, in order to give some result that is actually reasonable, we need to do the so-called localization. And by that, you get the Nekrasov partition function. It's first developed by Nikita Nekrasov. It changes this integration into the so-called equivalent part. And then once you do the equivalent part, you can change the integration into an ensemble sum, just like a statistical mechanics. Now, each of the state in your statistical model is labeled by the so-called Young diagram. So it's a 2x2 diagram, which is labeled by lambda. And then you have this expansion over the power of lambda. So the size of lambda is essentially how many boxes that you have. And you have a pseudo measure which is given by the localization. And we'll call this in 1, the expectation value of 1. So here, you can consider it's a statistical model, and this thing is the measure. And here, you don't have any observables, so you just put 1 here. And A, the subscript A means that we are choosing the vacuum according to the set of the Coulomb modular parameter. Okay, so this is the bulk theory that we are considering. How about the defect that we want to do? So we consider two types of half BPS defect in the 4-dimensional SQCD. So half BPS means that you kill half of the supersymmetry. So you originally have 8 supercharges, now you have 4 once you do this. There are 2 types. The first one is called canonical defect. You can do this by just adding additional D brane in your string theory construction. And the second one is called the monodromy defect, which can be done by putting your theory on an OB fold. So one way you can do this for the canonical defect is you take the following so-called gauge origami configuration. So instead of 10 dimensions, so in 10 dimensions, you split out the rest of the 2. And now instead of using a D4, you use a D3. So it's like you take a T duality. You have three sets of D3 branes. The first one is where your physical space lives in. It's a 4-dimension. And then you now introduce additional D branes, which intersect your physical space in your 2-dimensional subspace. So if you integrated out the additional degree of freedom in the 4 and 5 direction, you ended up with a physical theory and with something which filled in either in the first 2 real plane or the second 2 real plane. So by doing so, you can construct a codimensional 2 canonical defect. So codimensional 2 means that it's 4 minus 2 equals to 2. By introducing a so-called D3, 1, 2, so that's your physical space, and an additional I3, and I can be either 1 or 2. Now the additional D3I3 brane inserted can be viewed as a U1 gauge theory with a modular parameter X. So here, if you instead integrating out 4 and 5, I can say, okay, let's integrate out 1 and 2. And now this D3, 2, 3 becomes your physical space. So there's a symmetry between all the three. Now, the D3I3 brane, after you integrate out the additional freedom from the 4 and 5 direction, it becomes a codimensional 2 defect after, as I said, integrating out the outside physical space. And it's called QI observable. You have two of them. It can be either Q1, which occupies the first complex plane, so that's like 0 and 1. So here, I'm labeling the real space into a complex plane. So this is the first complex plane, 0 and 1 give you the first complex plane. 2 and 3 will give you the second complex plane, and so on, and so on. So essentially, just writing R10 equals to C5. So there are two cases. You can have your defect on the first complex plane, or you can have your defect on the second complex plane. And the good thing is, because you are preserving the same supersymmetry of the, when you're doing the localization, so which means that all this Q that you get, you can also do the localization calculation. I will not show you the detail, but it turns out that the expectation value of Q in your original supersymmetry gauge theory can again be expressed as an ensemble over an equivalent statistical model. You have the same pseudo measure, and then you just put the Q here. And Q is now evaluated in each of the states. Now, it can be proved. So we proved that this canonical defect that we just constructed is satisfied by the so-called quantum TQ equation. So you have this equation 4. So you have Q, which shifted the argument by an epsilon, depending on which direction that the defect is put it, plus, and you have a second term, which involves all the masses in your gauge theory. And also you have involved this gauge coupling Q. And then another Q function, but then with shifted in the opposite direction. Well, equals to a T, which is a polynomial, a degree n polynomial in this parameter x times Q. Now, in the case if I equals to 1, and you can take the epsilon 2 goes to 0 limit. Now, in this way, you will recover the two-dimensional n equals to 2, 2 supersymmetry on the first complex plane. And then the quantum TQ equation becomes the so-called Baxter TQ equation of the integrable system. So now you can write, you can basically remove the expectation value, and you just have a single Q. And you have some shifted operator acting on it. Okay. And the second defect that we want is the so-called monodromy defect. Yes. Sorry? Oh, so first of all, you can change, say, if I equals to 2, but then you take epsilon 1 goes to 0 limit, then of course, that is just a symmetry. Now, the interesting thing that you mentioned is if I equals to 1, and then you take epsilon 1 goes to 0, or I equals to 2, you take epsilon 2 goes to 0. Now, the Q function that you have is singular when you take epsilon 2 goes to 0. So in that case, you cannot just simply remove the bracket. So there's a way that, a more complicated way that how can you remove the bracket when you take I equals to 2 and epsilon 2 goes to 0. But it's not just as simple as for the I equals to 1 case. It's doable, it's just more complicated. So at the end of the day, you will still get the same equation. So here you replace epsilon 1 and epsilon 2. So here epsilon 1 with epsilon 2. You still get the same equation, just the whole process is more complicated. Any other question? Here? Oh, so the reason is this T also depends on the expectation value. So it also depends on the state. So that is why you cannot just simply take out the T. So this T is actually a degree, it's a codimensional 4 defect in this case. So it's like you have a C1, and then you have a codimensional 4 defect sitting in the intersection between C1 and C2. Now, if both of your epsilon 1 and epsilon 2 are non-vanishing, then everything is locked. So omega background is like you're having a rotation here, rotation here. So that is why you cannot move anywhere. But then if you take one of the epsilon parameter to 0, then in that case, this codimensional 4, this single dot here, can be now moved along the C2. So now you remove, that's why they can, they separated this T. So this T becomes this T, and you don't need to worry about this expectation value anymore. Any other question? Okay. So the second type of defect that I introduced is so-called monodromy defect. It's nothing really fancy. So remember, we are considering a gauge theory, so which means if we have a connection. So I can just say, okay, I'm going to impose a singular behavior on my gauge field A mu along, say, the first complex plane. So C1, which is R1 to 2, at the origin of the second complex plane. So I create something which looks like a Aharonov-Bohm effect by assigning the gauge field at the origin of the second complex plane to be in this form. Now, interestingly, proven by Kano and Tachikawa that the monodromy defect can be presented in the theory on the orbifold. So originally, your theory is living on R4. But now just say, instead of living on R4, I'm living on the first complex plane time, but the second complex plane is quotient by some Vn action. Now, when you do that, you create the so-called chainsaw quiver. So now you have a bunch of quiver nodes, and each of the quiver nodes will have a gauge coupling. So you have a fraction of this, we call fractional coupling Q omega, and then it relates to the original Q in your original box theory by the product. And now for later convenience, I will define both the U and gamma variables based on this fractional coupling U, Q. Now you can do localization. Again, you can perform the localization by the theory on the orbifold. In particular, there's a projection that if you start with the theory on the orbifold and you do the incident calculation, you get the incident moduli space with theory on the orbifold. And then you can now project it back to your original flat theory. Now, which means if you consider the incident partition function on the orbifold space, you can consider the pullback of the projection. So you integrate along the projection fiber first, and you leave up with the bulk term. And now you have some this monodromy defect psi. And then after that, you can integrate it over the flat space moduli space. So in this picture here, I will use the green color to represent the monodromy defect, which sits in the origin of the second complex plane and occupying the first. Now we can play with the defect that we get. So the first one we consider is in the award-winning paper, is the so-called intersecting defect. So I can just place a monodromy defect in the first complex plane, and the second canonical defect, so you can see there are different colors, in the second complex plane. So they intersect at the origin of your four-dimensional space. Now remember, if you just have the red canonical defect, you have the so-called Q function. Now, in the presence of both the red one and the green one, the canonical defect, the monodromy defect, what happens is now you create just like the coupling. Just like the coupling, so you split from one original coupling to a bunch of them. And now you will have, now again, you will have a bunch of Q observables. And they will obey, this omega runs from 0 to n minus 1. So that's actually the in which representation of the Vn orbifold that you are doing. And then they will obey this, this periodicity condition. So if you shifted the index by n, then you shifted the argument by an epsilon 2. And the last one, so you have n minus one, n of them. And the last one corresponds to the bulk, your original Q that when you don't have the green or monodromy defect. Now again, through the localization, we found that the correlation function of this fractional Q, so this Q now takes value in this orbifold space, and the expectation value is using a double arrow. They'll satisfy the so-called fractional TQ equation. So now instead of shifting the argument directly by an epsilon 2, you shifted the index by 1 every time that you move. And once you pass through the whole cycle, you use this periodicity and keep on going. The second way that we can play with the defect is so-called the parallel defect. Now, it turns out that for the parallel defect, in order to give us something meaningful, we don't just impose one canonical defect in the C1, you actually impose n of them. So you have like n stacks of red here and then a single green. So what happens is each of the red one will give you a fraction of Q1, just like what happens in the intersecting case. So you have n of this fraction of Q, but now instead of having each individual one, you consider this combination of all of them. So this combination will again, you can again create n fractional, this curly Q function. And then the bulk one will be corresponds to the last one. So the bulk Q1 does not identify which any of the fractional Q. You need to take a proper product. And interestingly enough, we found that the same correlation function, so we found the correlation function for this curly Q also satisfies the same TQ equation. So here you can see that, again, you shifted the index by 1, shifted the index by -1, and you have the same, so here the T is written as an operator acting on this expectation value. Now, I would like to talk a little bit about the relation between the 4D n equals to 2 super QCD and the so-called Heisenberg spin chain. But so in order to do that, so remember that we have this fractional TQ equation. So it's a degree 2 difference equation in this index omega. So you can just change and rewrite the degree 2 difference equation into a degree 1 by writing it into a matrix. So you write down the matrix psi, which is built up from this. So if it's intersecting, you just use the fractional Q. If it's parallel, you use this curly Q that constructed. And with the proper gauge transformation, so which means just multiply some constant matrix in the front, we found that you can now shift this theta vector by L. So L is the Lux operator of the XXX spin chain. So here you will see the inhomogeneity on each of the sides, and then you have four components built from the 3 generators of the SL2 algebra. So let me, okay. So before our work, it's already known that the spin chain is connected to the n equals to 2, for the n equals to 2 super QCD. So the first hint is that if we consider the Seiberg-Witten curve of n equals to 2 SQCD, we found that it will collide with the spectral curve of the Heisenberg XXX spin chain. And the twisted superpotential of the n equals to 2 SQCD is identified with the Yang-Yang function of the Heisenberg XXX spin chain. So that's the second step. So Yang-Yang function means that you already consider quantization of the integrable system. And also point out the saddle point equation of the n equals to 2 SQCD partition function in the so-called epsilon 2 goes to 0 limit, sometimes known as the Nekrasov-Shatashvili limit. It will recover the so-called Bethe-Ansatz equation of the Heisenberg XXX spin chain. Now, let me have a quick review on on the spin chain. So the quantum SL2 spin magnet is a one-dimensional lattice. You have a nearest neighbor interaction. And the lattice model of unintersecting spin. So each of the spin, you have 3 generators of the SL2. You probably know them as S0, S plus, S minus. Usually sometimes people write as Z, as X, as Y, but then here I will use this notation. And the spin operator will obey the commutation relation, which I believe you are very familiar with. And you have a quadratic Casimir, which is built from the total spin, which is given by this, is a scalar. Now, usually when we learn in quantum mechanics, so we write down the spin in a vector form, so which means it's finite dimensional. But it's not the only way that you can satisfy this algebra, this spin algebra. So one good way that you can do is so-called Heisenberg-Weyl module. So you consider the operator, so the spin operator is a differential operator on some variables. So here you can see equation 16. I write the spin operator in terms of this differential operator acting on this variable gamma. And you can check that, yes, if you write the spin operator in this differential operator form, it indeed satisfies the spin operator relation. So yes, it's a representation. And what are these operators acting on? Well, it acts on the space of the Laurent polynomial of your variables gamma. And here you have one additional parameter that you don't see in a finite dimensional representation called A omega. This fractionally or A omega. So you consider A as an anchor or a reference point of your system. And then if you act S plus, it goes upward, increase the power of gamma. If you act S minus, decreases. Now, if alpha is not an integer, then you don't have any state which is killed by S minus. So which means this space by nature is usually infinite dimensional. Now there's another Heisenberg-Weyl module, which is written here. I use different variables, U. Now you can see the S0 are basically the same, but then S minus and S plus are different, even though both S plus will increase the power of your variable and S minus decreases. But the two is actually not equivalent. So now you have 2 Heisenberg-Weyl modules that you can write on your spin. Now the Hilbert space of the quantum spin chain is nothing but a tensor product of local individual Hilbert spaces of an individual spin chain. So you just take a tensor product of those. Question? So I will going to use both. Yes, actually so this is the one that if you do the intersecting case, you get this module, the one in the front in equation 16. If you do the parallel one in our paper, we got 17. So actually the 2 is related by a Fourier transform between U and gamma. So essentially you get the same in that spirit. Yes. Okay. So the Heisenberg-Weyl module is generally an infinite dimensional, irreducible representation over the Youngians of the SL2. Now, you can fine-tune your S. So suppose your spin S is a half integer, and your reference point A is an integer. In that case, you can do a quotient, and then you get your familiar finite dimensional representation. If your spin is not necessarily integer, but then you fine-tune your A, then you get Verma. You can either get the highest weight or the lowest weight. Now, as I just mentioned, as by Dario, if you do an intersecting defect like this, then you get the Heisenberg-Weyl module written, the first Heisenberg-Weyl module. And the spin, the reference point and the inhomogeneity of the system is related to the masses, the fundamental masses of the theory, and also by this the remaining omega parameter, which will be identified with h bar. So it's essentially the Planck constant. Now, if you do a parallel defect, you get a different Heisenberg-Weyl module. Now, here the parameter matching are almost the same, but they are not. They are almost the same, but not identical. So here, if you can see, this is omega plus 1 for the n plus, but then here is omega. So it's a two different kind of spin chain. And now we got the Hamilton. We got the Lux matrix. So for the Lux matrix, we can build the monodromy matrix of the system. And you have a special twisted matrix K, which depends on the gauge coupling of the theory. It will transport your first theta to its shifted by this epsilon 1, which is essentially h bar. And the generating function of all the commuting Hamiltonians is nothing but the trace of the monodromy matrix. You can get a special curve, which is given in the form that you have the first term, which corresponds to shifted by the epsilon 1, and then the generating function of the Hamiltonian, and then finally, this part is essentially the determinant of the monodromy matrix. Now, in the defect case, you can just simply take epsilon 2 goes to 0. And now you can split the bracket between the correlation function between the surface, the monodromy defect and the canonical defect. And now you have the special curve, which acting on just the product, not the correlation function anymore, just the product between the monodromy defect and the this canonical defect. Interestingly, remember that the canonical defect in the epsilon 2 goes to 0 limit itself obeys a TQ equation. It's just you don't have psi. You just have it's just obeyed by Q itself. So now you can multiply the second equation by psi, and you take the difference between the two. And now since Q has nothing to do, this x is a parameter that you can tune, so which means it's going to hold for all x. So you can just divide it by Q. You don't need to worry about Q going to 0. And we can prove that the monodromy defect is actually the wave function of the x. So that's a typo. It's xxx, not xxz. It's xxx spin chain. You have all the generator function of all the Hamiltonian acting on psi equals to here. This is the generator of the chiral ring. So here everything is a constant. So we essentially prove that yes, psi is actually the eigenfunction of all the Hamiltonians. Okay, I have 17 minutes. Okay, so this is the part. So far I've mentioned what is the relation between supersymmetric gauge theory and integrable system. In this case, it's the XXX as an example that I showed you. And the other one is the relation to the conformal field theory, which is we are going to use the Knizhnik-Zamolodchikov equation. So the first realization is by Nikita Nekrasov and Simbaluk that in the same year that we published our paper. So the idea is if you just look at the monodromy defect alone, they prove that they satisfy the so-called 4-point Knizhnik-Zamolodchikov equation of the SLN current algebra. What does it mean? It means that now you have a conformal field theory. You have 4 parts. And you can, by conformal transformation, you can always you can always fix 3 of the points to 0, 1, and infinity. So now you have the last point, which is related to this gauge coupling Q. The theory is characterized by 2 n parameters. You have the lowest weight Fermat module at 0, and you have a highest weight. You have 2 n minus 1 highest weight Fermat module at infinity. And then in the middle, Q and 1, you have 2 Heisenberg-Weyl modules characterized by a single parameter mu, which are related by the sum of the half of the masses minus the sum of all the Coulomb parameters. So if you do as you this A is just 0. So by doing so, we prove that, Nekrasov and Simbaruk proved that the psi is expectation value for monodromy defect without taking any limit. It's actually the 4 conformal block of this particular conformal field theory. And interestingly, because they didn't do any of the restriction, so that means the level of the SL and affine algebra is associated to, of the conformal field theory, is associated to this ratios between 2 omega background parameter, epsilon 1 and epsilon 2. And these two can be complex, so which means their ratio can be also complex. So what they had done is they found an origin of an analytic continuation of a conformal field theory where their spins, their weights, and even their level can be complex. Now, we can consider the Fourier transform in the fractional Q2 function. So remember, the fractional Q2 function is we have an intersecting defect. So you just organize them into this n by 1 column vector. And then you take your Fourier transform. We call it H. And we prove that this H2 will satisfy the 5-point Knizhnik-Zamolodchikov equation. Now, because it's 5-point, on top of the original 0, 1, infinity, and Q, we now have an additional point Y, which comes from the gauge theory side. It comes from the Fourier transform of this parameter X of the defect. And we can now check which representation, so which representation the vertex algebra is, the vertex is for this location Y. And we found that in this case, you get the standard n-dimensional representation of SLN algebra. Now, in the parallel case, again, you can consider both of the defect. You again take a Fourier transform. But now, because you have, so remember in the parallel case, you have n. So you have n canonical defects. So each of the canonical defects will give you a parameter, a Coulomb modular parameter x omega. So here, if you take a Fourier transform, you have n parameter with Fourier transform to another n parameter. So now you have all these fractional y's showing up. You can write down y as a ratio of mu, just like what we did for the fractional Q coupling. And the bulk y will be, again, related to the product of all these fractional y's. And through some tedious but rigorous calculation, we proved that this H1, so in this parallel defect case, the correlation function will satisfy the different 5-point Knizhnik-Zamolodchikov equation. So the first different thing that you can see is here you don't have the coefficient is 1 for the parallel defect, while in the intersecting defect you still have these ratios between epsilon 2 and epsilon 1. And secondly, we can look at the representation of the puncture at Y. So what it gives? We found that it gives the so-called twisted vacuum module. So what is a twisted vacuum module? So the Verma module is that you have one ground state which is killed by half of your generators. But here, you consider the case which is like instead of using the ground state, you use a different state to generate. It kills not by half, like slightly different half of the generators of your algebra. Now, in the epsilon 2 goes to 0 limit. So, in the epsilon 2 goes to 0 limit, again, the here, so first thing, you don't need to worry about this equation anymore. So you just look at the second one. And here, again, you can remove the bracket. And you get, this is the Gaussian Hamiltonian. So you have a Gaussian model defined on three, is a three-side Gaussian model. So you have at 0, at 1, and at q. Okay. So any question before I move on? Okay. Yeah, it's yeah, I can imagine it's a bit overwhelming. So quick summary. So we studied a two half BPS surface defect, the canonical defect and the monodromy defect in 4-dimensional n equals to 2 SQCD. And the correlation function of the two half BPS defect, both parallel and intersecting, obeys the fractional TQ equation, slightly different version. But then you can use both to construct the Lux operator of the XXX spin chain with two different kinds of spin chain. And both of them are in the Heisenberg-Weyl module of these Youngians of SL2. So both of them are by infinite representation. And the monodromy defect alone is the 4-point conformal block of the SLN current algebra. So this is not proven by us, it's proven by Nekrasov and Simbaluch. And we expand on that. We found that if you Fourier transform the intersecting defect correlation function, and then you get a 5-point conformal block of the SLN current algebra, with one of the vertex appears to be the corresponding n-dimensional standard representation of the SLN. And if you do the parallel defect and you do a Fourier transform instead, you get another 5-point conformal block. But now the 5th point is the twisted vacuum module of the SLN algebra. So thank you for your attention. I hope you are not being overwhelmed.
Question.
Yep.
First, yeah, I don't know if I'm overwhelmed or not, but so if I understand correctly, so you have both XXX and Godin model
Yes.
that appear either from parallel or intersecting. So,
Yes.
yeah, and the two are related by some Fourier transform. So if I go to 5D.
So okay, one thing is if you do an intersecting case, because if you look at the equation for the intersecting one, if you take epsilon 2 goes to 0 limit, your Gaussian equation will just vanish. Here, the function will just become 0. The coefficient just becomes 0. So in the intersecting case, the way that you got Gaussian is a little bit weird. While in the parallel case, because you don't have epsilon 2 here, so you can safely take epsilon 2 goes to 0 limit. And the point is, for epsilon 2 goes to 0 limit is where your best gauge correspondence established. If you don't, for general epsilon, you don't really have, you don't really have that, that correspondence.
But so my question is, if you lift all this to 5,
yes.
Can I see this as type 2B duality related or parallel?
So that's actually one of the projects I'm working on right now. So if you uplift everything to 5D, so instead of having Gaussian in XXX case, you have an XXV to XXV correspondence. And in that case, you can actually construct both, at least in the parallel case.
I see. So, so what do you want to do?
So in that case, you don't really need to do the Fourier transform. The parameter just goes one direction to the other. They use the same parameter.
So second question. Can you construct the backstack Q open?
The backstack Q operator is the canonical defect. Yeah, so if you do the canonical defect either in the first or second complex plane, they'll satisfy the quantum TQ equation, and that gives in the epsilon 2 goes to 0 limit, you get a backstack Q
So
operator.
this is the Q point. Maybe presumably using your vectors psi, you can build something like the matrix that contains.
Yeah, I think it's doable. So this Q here is, yeah, as I say, it's more like an eigenfunction of the Q operator.
So have you done this? Backstack?
Yeah, I think that's what happens. Okay. Yes, the gentleman in the back.
Well, yeah, pointed out a long time ago, so how do you sort of see that?
So in the parallel case,
Objects like, for example, operate, I think, if expected that for net, we see those would not.
yeah, so for instance, if you take the parallel case here, you take epsilon 2 goes to 0 limit, you're left with the second equation, right? And those A's are now the three size Gaussian operator. And you can, now all of these are still n by n vector. So now you can condense them, you're solving this n equation, and you condense them and get your generating function. And then now you have the spectral duality. Since now this H here, so H is a Fourier transform of this fractional Q, but in the epsilon 2 goes to 0 limit, you isolated out the Q or Fourier function of Q times psi. So you actually prove that the XXS and Gaussian share the same eigenfunction, which are this monodromy defect from the gauge theory. Yes. Yes, they are related.
Question, let's thank our speaker again. So there will be a short break. I think you can get some water on the first floor, and our second talk will begin at 2:15.